So, in this week's programming tips videos, we're going to investigate classes some more and objects. First, we'll look at a bunch of common mistakes that people make with them. Secondly, we'll look at mutation using classes and objects. And then third, we are going to introduce a new way of using loops. We've previously seen for loops and list comprehensions. This time we're going to also see while loops and see how they differ. So this week we introduced classes and objects. And so let's work with a class here that contains lots of errors and explore a bunch of the common mistakes that we see people making with defining and using classes and methods. Okay. So the idea is we're going to define a ball and then we're going to get back its position. Okay, not very complicated conceptually here. And the first mistake that we find is that get position is not defined. Well, why not? Here's a definition right here. Well, it's looking for just a function definition that's outside of any class. Okay, how do we tell it that it's in here? Well, we need to tell it, okay, that B is the object of this that we want to get the position of, but we don't provide it as an argument in that way. Okay, we need to provide the object up here, object dot method name. Okay, all right. Well, let's run that now. Well, we still get an error. Okay, but different error message that says get position takes exactly 0 arguments. Okay, here 0 arguments, and 1 was given. Well, there's nothing inside the parentheses here. Well, we are kind of giving an argument, the ball, the B here. So while the convention is to put the B up here, that's what we have to do. Okay, we need an argument here as well, and that's where we put self, if you remember. Okay, that the methods all take this argument called self, which is actually the object that you're working with. Okay, all right, run that again. And here, position is not defined. Well, why not? Well, because the object self has the position, and so we need to tell it that it's self.position. Okay. But the ball object doesn't have a position, it says. Well, that's because when I created it, I didn't actually give it a position. In fact, I really did the creation completely wrong here. So first of all, the name of the constructor, the method that gets called when you want to construct or create a new ball here, a new object, is not called the same thing as the class or something else like that. It's called underscore underscore init underscore underscore. Okay, it's just always called that in Python. Okay, so I fixed that, but well, let's see how far that gets us. Okay, and it takes exactly 2 arguments. Well, I've provided, there's 2 arguments up here, but 3 were given. Well, 1, 2. Well, what's the third argument that was given? Well, implicitly, it is the object that is being defined. Okay, it's a little bit confusing, but implicitly, it gets the object as well. Just like in this method, it needed the self as a parameter. Here we need self as a parameter as well. Yeah, if I can spell it correctly. Okay. Attribute ball object has no attribute position. We saw this before. Well, it's because just like here I want to say self.position, up here I should be saying self.position. And similarly self.radius. Okay, and run. Ooh, I actually got a result. No error. Yay. So it worked. It did what it's supposed to. I gave it a position at the origin, 0, 0, and it returned that position. Okay. But there are a couple things I still want to fix here. Okay. One thing that's not obvious is that the init method is special. You don't need to return anything. In fact, now with all these changes, returning ball is just returning this class, whatever returning a class might mean. But actually, ball here, okay, the constructor, is returning an actual ball. It's really ignoring what I'm telling it to return here, because implicitly, the init method always returns the object that's being created. Okay, you don't need to do it explicitly. It's just automatically being returned. Okay, so I got rid of that return statement. Let's make sure it's still working. Yes. Okay, so this actually is correct, but I have one little thing that I still want to change. Okay, class name. Typically, convention in Python is to capitalize the class name. Okay, so I'm going to capitalize that. And run that again, and it still works. That's good. So, we had lots of mistakes, but this is what a typical tiny little example of a class and object usage would actually look like. Okay. Once again, everything has to use self in here to refer to the object. Out here, you put the object name dot function, or excuse me, method name that you're using. Okay, thanks. So now we're going to look at mutation using classes and objects. So the short version of the story here is going to be that we saw mutation with lists. We can do the same things with classes and objects. Okay, but I'm going to show you an example illustrating that. Okay, so what I have here is a class with a few methods defined. In particular, a point has an x and a y component, and I have methods for changing and getting the x component. So I can create a point P, and well, I could create another point Q that is also 0.45. And I could also create have another point R that is simply going to be P. Okay, and so right now I could print P dot get X and Q dot get X and print R dot get X. And they better all be the same thing. They all better have 4, yes. Okay. But what happens if I actually change the value of P's X? Okay, so I say P dot set X to be 4, excuse me, 10. And so P's X has the value 10, but so does R, because R is actually the exact same object as P. Okay, or when we were using reference diagrams, we had P and R really being arrows to the same object. That's what's going on here. Whereas Q is a reference to an object that just happens to have the same values initially, 4 and 5. We've been using for loops and their special case list comprehensions. They're great, they're very useful, but they have a limitation that sometimes we don't want to put up with. For loops, you always say for I in some data structure, okay? And the number of times that you loop is the length of that data structure. Okay, so you know how many times it's going to loop beforehand, okay, the length of that. So what if we want more flexibility? A while loop will provide us with that flexibility, and we'll see that in the next couple examples. So first we're going to have a simple while loop just to illustrate how you use them. Okay, we're going to define a function called countdown that's going to, if you give it the value 5, it'll go print 5, 4, 3, 2, 1, 0, and then stop. Okay, so what I'll do here, I pass in n. Okay, I want to initialize some variable I to be n. Okay, and while I is greater than equal to 0, what I want to do is print out that value and decrement, okay, or subtract 1 from it. Okay, so let's see what this does here. that tested out countdown of 5. Run that, and it does exactly what I described. So how is it actually doing? Well, I is initially 5. I is 5 greater than equal to 0. Yes, do the body, in which case I is now 4. Is 4 greater than equal to 0? Yes, print that out. Decrement. Is 3 greater than equal to 0? Yes, continue. Okay, a couple more iterations. Is 0 greater than equal to 0? Yes, do the body. Decrement. I is now equal to -1. Is -1 equal to greater than equal to -0? No, we stop the loop. Okay. Now, for this particular example, we could have also done this with a for loop. Okay, I could have written here for I in range, start with the value in, and go to -1, and we stop before -1, in other words with 0, and we count by -1 and print out I. Okay, and run that, and we see it does exactly the same thing. The nice thing about the while loop over the for loop in this example is that the for loop is building up this range, which is a data structure, a list of size n. Okay, and if n is big, then that list is big that it creates. Whereas the while loop is just using a single number. But more to the point, the while loop is just repeating, while some condition is true, and it could be doing something really fancy in the body, as we'll see in the next example. So even before we introduced for loops, we did kind of a funky example in one of the quizzes where we used timers to iterate over computation, because as timers repeatedly call their timer handler, you can repeat computation in that handler. Okay, and so an example that we did there was something known as the Collatz sequence or Collatz conjecture, which is a perfect example for a while loop. Okay, the idea was you start out with a number. If it's even, what we're going to do is divide by 2. If it's odd, we multiply by 3 and add 1. Now, the question is, when we do that computation over and over, do we ever get down to 1? Okay, and the answer is, well, for everything that we have ever tried, yes, but we haven't been able to prove it for all numbers. So in particular, for any starting number, we don't know whether it's going to stop necessarily. So, for loop is inappropriate. We need to repeat while the number is greater than 1. So let's write some code for that. Okay, so I'm going to start off with I being our number, initialized to the number that's passed into the function. Okay, and then I'm going to say while I is greater than 1, okay, because we stop when we get to 1, and we happen to know that you can never get 0 or a negative number here. Okay, you can look at the mathematical properties of this and prove that. While I is greater than or equal to 1, well, I want to print out the current number, and then I want to change the number if it's even. So if I mod 2 is equal to 0, that means it's even. Then what I want to do is divide I by 2. And otherwise, I'm going to multiply 3 times I and add 1. Okay, and we can try this out on some numbers. So for example, Collatz of 5 starts out with 5. I is 5, that's greater than 1. We repeat. We multiply by 3, add 1, get 16. Then we divide by 2, we divide by 2. When we divide by 2, or when we divide 2 by 2, we get to 1. Ah, we're done because 1 is not greater than 1. And that's the end of the sequence. Well, what about other numbers? Collatz of 1000. Okay, is a much longer sequence, but it indeed does stop as well. So play around with this, it's kind of fun, but as an example of a while loop, we're repeating some computation, even some fancier computation, while some condition is true, and we don't know when it's actually going to end, if it actually will end. So as a last example, let's consider this nasty little while loop here. So I is equal to 1. While I is greater than 0, I'm going to increment I. So I just keeps getting bigger, and I greater than 0 is always true. So basically, this is going to run furiously in pace, just counting up, counting up, counting up, counting up. Okay, when will it end? Never, right? Well, except, aha, we have a timeout. We program exceeded runtime limit. We impose a 5-second time limit because otherwise, if we didn't, the browser would just keep going, 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 calculating here. And what would happen is your browser would freeze up because we're running everything in the browser, and you would lose everything in your browser, including whatever code you're running. Okay? We don't want that. And none of the programs that we're going to write in this class should take more than 5 seconds, so that should be fine. Now, if you happen to be writing, calculate the millionth digit of pi in your code, well, you would run over 5 seconds, but, we're not going to be doing anything like that in this class. So, if you ever run into this time limit, what's probably happened is you have some version of a loop, probably a while loop, that's just going on furiously forever.